Okay, I think we can start. Let's get started. Welcome to fourth meeting of modern SSD course. So today we will review today Rakesh, another supervisor of this course. Sorry, yeah. So Rakesh, another supervisor of this course, will deliver introductory lecture on MQSim. So let me allow Rakesh to share his screen. Okay, Rakesh, the stage is yours.
Thank you, Dr. Park. Yeah, so let me share my screen. So can you see my screen now?
Yes, but not, yeah, okay, so I can see your screen in presentation mode.
Yeah, thank you. So hi, my name is Rakesh Nadig, and today I would be giving a brief introduction to MQSim. Here is a brief introduction about myself. I am a PhD student at Safari Research Group since 2021. Prior to joining my PhD, I was a senior staff engineer at Samsung Electronics India for a period of 7 years. And I have received my master's degree in electrical and computer engineering from University of California, Irvine. Here's a list of my research areas. I am interested in memory storage systems, NAND flash memory, hybrid memory storage systems, machine learning, and near storage processing. And this is my email address. Please feel free to contact me on this lecture or anything in general. Let's look at the outline for today's lecture. So we'll briefly look at the internal components of a modern SSD. This will help us understand what a simulator or a SSD simulator needs to model to understand the performance of a modern SSD. And then we also have a brief look at a brief introduction to MQSim, and we look at the core mechanism of MQSim. Then for the project, we look at the code structure and how to configure the MQSim. So let's jump into the internal components of a modern SSD. So a modern SSD actually has two parts to it. One is a front end and a back end part. And so the back end part is mostly consists of the storage medium, which has the memory chips. So there are a number of memory chips which are connected to different channels, and each memory chip will have a number of dies in them, and a die can have multiple planes, and each plane will have a number of blocks which constitute a large number of pages. And these are all connected through a bus interface. And generally in storage we can have typically we have NAND flash memory, but we can also have other technologies like PCM, MRAM, or 3D Expoint. Then we have the front end, which houses the management and control units. So we have the host interface logic, which implements the protocol that is required to communicate with the host system to which the device is connected. And it has a device level IO request queue, which to which all the requests come from the host. And these requests are then passed on to the flash translation layer, which manages the resources of the SSD and also processes the IO requests and performs some background operations. And then we have the flash channel controllers, which sends commands to the backend and also sends data to the backend and receives data from the backend. So let's look at the FTL in particular and see how it manages the SSD's resources. So the main task of FTL is to perform the address translation, which is converting the logical page address to the physical page address. And that is the reason for doing that is because the flash writes can only be performed on pages that are erased, which means that in a NAND flash device, the updates have to be performed out of place, which means it cannot be updated on the same page. So it has to be written to a new or a different free page. and the old page has to be marked as invalid. And this also involves updating the logical to physical page mapping, which is a table which maintains all the entries of logical to physical translation, and that also uses a cached mapping table which is stored in the DRAM, which stores all the recent mapping entries. Then, so once a few blocks are having a lot of invalid pages, then the garbage collection process is triggered, which reclaims the invalid physical pages, and this is done in the background and of the critical path. We also have a write cache, which is used to decrease the resource contention, and this also reduces the latency. The write cache is where the data gets written to, and the host can prepare an acknowledgement immediately, and the writes tend to be written gradually, the backend. So these are the main components of a modern SSD, and the MQSim actually models them in the simulator. So let's look at let's look at the introduction to MQSim. So as we discussed just now, MQSim is a simulator which accurately models conventional SATA-based SSDs and modern multi-queue SSDs. So it implements multi-queue protocols like NVMe, and it supports steady state behavior with preconditioning. Here by steady state, I mean the simulator can prepare the SSD to reach a state where the data cache is warmed up, and it also triggers the garbage collection process. So a large amount of data is written to prepare in the preconditioning process to prepare the SSD so that the SSD performance can be evaluated in that manner. So we also MQSim also models the end-to-end request latency. So it models the request latency from the host till from the command which the request which is sent by the host till it reaches the backend, and and vice versa. So we'll also MQSim also has a very flexible design, which means that the components of the MQSim is written in a modular fashion. So any new component or a policy that needs to be added can be added in a very easy manner. And it also has the ability to support emerging non-volatile memory technologies like 3D Xpoint, PCM, etc. And MQSim is completely open source, and this is the link to the Git repository. Just a moment. So this is the link to the Git repository, and it's completely written in C++. So let's see how multi-queue protocols are implemented. In a conventional host interface, for example, SATA, it's used mostly in magnetic hard disk drives and in low-cost SSD devices. The throughput of the device is lower compared to the NVMe protocol. Here we have software I/O request queues per core. So if we have multiple cores, we have request queues per core, and there is a I/O scheduler in the operating system, which actually handles the scheduling. And it also has to ensure the fairness control for between the I/O requests of multiple cores, and it puts the requests in a hardware dispatch queue. And the SSD device consumes these requests from the hardware dispatch queue. Let's look at how a multi-queue SSD protocol works. So here, the NVMe protocol is a modern host interface protocol, and this takes advantage of the SSD throughput by actually avoiding the OS intervention. Here, we still have per core queues, which are hardware I/O request queues, but then it directly interacts with the SSD device, and the OS does not have to do the scheduling and the fairness control. So let's see how MQSim models the end-to-end request latency. Here we have different layers through which a request has to pass through, and we have the user application which sends a request, or which enqueues an IO job into the submission queue, which is in the host memory. And from the host memory, the IO request has to be transferred to the device, to the host interface logic or PCIe protocol. And from the the queue in the host interface logic, the request is a large request is broken down into smaller requests and is passed on to the SSD firmware, and the SSD firmware does the address translation, which from logical address to the physical address, and transfers the request to the NAND flash chip. So then the actual flash read process takes a considerable amount of time, and that is usually called as TR. And so once the NAND flash chip, the read happens in the inside the NAND flash chip, and the data is available in the internal page buffer of the NAND flash chip. The data has to be, a command has to be sent to get the data out of the NAND flash chip to the SSD controller. And this is the data transfer that is shown in the step 6. And then from the SSD firmware, the data has to move back to the host through PCIe data transfer. So let's see how the amount of latency that is added for when the data moves from each across each layer. So we see that the actual flash read and the data transfer from the NAND flash chip to the firmware or the SSD controller takes a substantial amount of time, and all these latencies are modeled in MQSim currently. So let's look at the SSD Back End Model. Here we have 3 major latency components which have been modeled. One is the address and command transfer to the memory chip. And then we have the execution time of flash of the read and write operations for different NAND technologies. It could be 1 bit per cell, 2 bit per cell, or 3 bit, which is SLC, MLC, and TLC. And we also, MQSim also models the data transfer from the controller to the memory chips, and also back to the controller. So in MQSim also has implemented die and plane level parallelism, which means that the commands can be sent to multiple dies, and it also supports multi-plane operation. And MQSim also supports advanced command execution. One such command is multi-plane operation, and there are other commands like copy back operation as well. Then MQSim also supports, also decouples the size of read and write operations. So the read and write operations need not be done at the same granularity, so which helps the performance of the SSD. So here the write operations can be done at the page size, which is typically around 16 kilobytes, and the read operation happens at a sub-page level, which means it can be even done at a 4K granularity, 4 kilobyte granularity. So let's look at SSD Front End Model. So as we discussed, the MQSim implements both NVMe multi-queue protocol and SATA native command queue protocol, and it also supports different priority classes for the host side request queues as per the NVMe standard specification. So it supports up to 6 priority classes. So for each queue, so it can be urgent, or it can be a normal priority, which uses a round robin manner protocol. So there are many priorities which can be used to configure the host side request queues. And there is also a data cache manager, which is a DRAM based cache with the least recently used replacement policy to cache the recently accessed data. And the front end model also includes FTL components, which are address translation unit, the garbage collection and wear leveling unit. And there is also a transaction scheduling unit, and the support for multi-flow request, which is basically the NVMe protocol. Please stop me if you have any questions at any point. So we can briefly jump to the mechanism of MQSim. So MQSim is a discrete event-based simulator. So so each operation performed by MQSim is an event, which means, for example, command address transfer is an event, or even getting the data out of the backend is also an event. Even sending the request to from the host to the host interface logic is also an event. So all these events are maintained in a red-black tree, uh, and they are ordered in the basically they are stored in the order of their completion times. So the next event which has to be completed will be the first one to be stored in the RB tree. And each node of the RB tree has a key which indicates the timestamp to finish, and the value is a callback function. So for example, if we are currently at simulation time 5, and a data transfer event starts, and it takes around 5 time units to complete, the simulator will insert a node in the RB tree with the following key and the value, which is 5 plus 5, and the callback function which the engine has to call to mark the completion of the event into the tree. So at each simulation cycle, or at each simulation step, the simulator will find the node with the smallest time value and set the timer to that timestamp and execute the callback function. So the event which has to be triggered next will always be called at the time when the simulation reaches the timestamp, and the callback function is called. So MQSim supports real disk traces, which, for example, MSR Cambridge block IO traces, or YCSP traces, and even user generated traces. And also it can generate its own traces, or these are called synthetic workloads, and it supports both kinds of workload environments. So let's look at the initialization of MQSim. So all the components which we saw in the modern SSD, or even in MQSim, are represented as classes, and these classes are objects, and they are maintained in the map. And the objects in the map are iterated through, and the corresponding functions are executed during the initialization. So each object that is in the map will have to implement some functions which the engine will use for the simulation engine will use for during the initializations. For example, setup triggers, or start simulation, which start simulation is the function which gets called for every component during the initialization process. So this is a snippet of the code from the MQSim, which will show how these objects are stored in an unordered map, and they will be iterated through, and the corresponding functions are called. So setup triggers is called, and validate simulation config and start simulation. So this happens during the initialization process. So for every component, this process will happen. So for example, let's look at start simulation. So start simulation basically looks at the event tree, or the RB tree. Here the event tree node is the RB tree node, and it gets the node with the minimum timestamp, and then it has to fire the callback. So here the callback is the execute simulator event, and this callback will be triggered when the timestamp is reached by the simulation. So So as we saw here, the callback function is the execute simulator event. So each function, each component in the MQSim will have to implement this execute simulator event, and when the node gets added to the arbitrary, the callback function gets executed once the event is completed. So how do we register an event in MQSim? So there is a function which is provided by the simulator, which is called register sim event function, which takes the following input: when the fire time, the target object, and parameters and the type. So here, if we see, it creates a new simulator event and then adds the simulator event to the event list. This event list is an alias for the arbitrary that we discussed in just now. So this is the register sim event, which has to be used for registering an event. And for example, if we need to register an event for sending the read command and address, we need to write the code in the following manner. So this is a snippet of the code from MQSim, and here we see that the register sim event is called for sending the command and address, read command and address, and the timestamp provided is the current simulator time plus suspend time and the latency that is taken for that the read command transfer takes. And this is on the current object, which is the class in which this function is implemented, and it then passes the die to which the command has to be sent. And this is the parameter that is passed for the callback function, the read command address transfer. So this is how we we register a simulator event. So now these are basically the main components of the simulator engine, and we can see these functions repeatedly being used in the MQSim. Now let's look at the code structure, how MQSim code is designed, and what are the different files that needs to be seen while implementing while using MQSim. So here we see on the right we see a directory structure of the MQSim when you download the code from the Git repository, and this is the root directory, the files in the root directory. So we see two XML files. One is called the SSD config, and the other one is called the workload.xml. So the SSD config.xml is a configuration file that is used to provide the preferred SSD configuration for the simulator. In a few slides, we'll see what is the structure of the SSD config.xml. And similarly, we have a workload.xml, which defines the workload that needs to be used for our experiment. And we have the traces folder, which you can see here, which is the folder in which user-defined traces or some of the real-world traces have to be placed when we choose to go with a real-world workload. And we also have, if you look at the source folder, we have a bunch of folders in which the main classes of the simulator are present. So we see that the sim folder is where we have files related to the simulator engine, and if there is a nvm_chip folder which contains the files related to the NVM chip, and it also contains files for representing a die, a plane, block, and page. And we have the source SSD folder, which is the most important folder in the MQSim, where it contains files related to the front end components which is the flash translation layer and the transaction scheduling unit. Here we have files related to the address translation, the garbage collection process, so etc. So then we also have the host folder in the source, which is basically related to files which deal with the real world traces or the synthetic workloads, and it also models the PCIe bus interface, so that those files are in the host folder. So then we look at a simple code flow, how the data moves from the host to the backend. And here, so the execution actually starts with the host. And as I mentioned, from the trace generation or the workload generation, and then it goes to the data cache, and to see if the data is available there, or to store the data there. And it also moves to the address translation unit for performing the logical to physical address mapping. And it then uh, goes to the transaction scheduling unit. From there, it reaches the flash controller and the NVM chip, which is the back end of the SSD. And the reverse, during the reverse of while reading the data from the NVM chip to the host, it follows the same steps in the reverse direction. So let's look at some of the important functions in each component. We in the data cache manager, one needs to understand the process new user requests. And in the address mapping unit, we need to look at the translate LPA to PPA and dispatch. The transaction scheduling unit has a schedule function, which is critical for understanding the TSU. And in the flash controller, we have the send command to chip, which prepares the command and sends it to the chip. So these are the important functions which needs to be looked into. Next we look at how we configure the MQSim for our experiments. So as I mentioned, there is a ssdconfig.xml, which is a SSD configuration file. So here we have many configurations which can be. So I have selected a few important configuration parameters here, but the entire list is available in the README file, which is in the Git repository. So we look at the parameters related to the host, and here we have the PCIe lane bandwidth, which is the PCIe bandwidth per lane in gigabits per second, and then we have the PCIe lane count, the number of PCIe lanes that can be configured. Usually the lane count can vary from 1 to around 32. So it can be 1, 2, 4, 8, and 32. So those are the values that can be provided here. And if you look at the device parameters, then we see the host. We can set the host interface type, which is the protocol that we need to use, whether it's an NVMe protocol or a SATA protocol, and the IOQ depth, which is the length of the host side IOQ, and the data cache capacity, which is the size of the DRAM data cache in bytes. Then we also have the option of ideal mapping table, which means that if it's ideal, all the mapping entries that are found in the DRAM, and there is no need to read the mapping table entries from the flash. So which means a very large mapping table can be accommodated in the DRAM. And we have the transaction scheduling policy, which is the policy used in the transaction scheduling unit. And here we have an out of order policy as defined in the Sprinkler paper, HPCA 2014. Or we also have the priority out of order policy, which implements out of order and with the NVMe priorities, as we discussed earlier. So let's look at some more device parameters. We can also configure the flash channel count, which is the number of flash channels in the SSD backend. Then we have the flash channel width, which is the width of each flash channel in bytes, and the number of chips per channel. Some of the NAND parameters that can be configured are what flash technology are we planning to use in our experiment, which could be MLC, SLC, or TLC NAND. And we also need to set the latencies for page read, page program, and the block erase latency. And these are currently in nanoseconds. So these are some of the parameters that needs to be set before starting our experiment. And we can also set the P cycles or the program erase cycles for each block. So this will decide the endurance of the block, and MQSim can also take this parameter. So some more parameters related to the NAND. We also have die number per chip and plane number per die. Die number per chip, we usually have multiple dies in a chip, and inside each die we have multiple planes, and we can also define how many blocks are there per plane and how many pages are there per block. So we can also define the page capacity in terms of bytes, and each page will also have a metadata part which needs to be defined, and the size of the metadata can also be provided in terms of bytes. So this is the SSD configuration file. Next, we look at the workload configuration file. So as I mentioned earlier, we have two types of workload generation. One is a trace-based workload, and the other one is a synthetic workload. So let's look at the trace-based workload now. So this is a snippet of a snapshot of the configuration file for the trace-based workload. If you can see, the XML contains the attribute IO flow parameter set trace-based, and so some of the parameters that we need to provide are the priority class. So we can define the priority for the host side IO requests, and we can also define the data caching mode, which here we define it as write cache. And we also need to provide the channel IDs, chip IDs, die IDs, and the plane IDs to which the workload or the experiments have to be performed. To which these are the NAND attributes which have to be targeted in this particular workload. It can be the same number as or the channel IDs, and all these IDs can be similar to the one defined in the SSD configuration, or it could be a subset of what is defined in the SSD configuration file as well. And then we look at the initial occupancy percentage, which is 70%. So this initial occupancy percentage means that we pre-fill the SSD up to 70%, so that process like garbage collection can be triggered when we run our experiment. And this is the file path is the important attribute in this XML file. It provides the path of the trace file that we need to use in our experiment, and this is an important attribute. And the percentage to be executed tells us how much percentage of the trace file needs to be executed in this workload. And if we define it as 100%, all the requests in the trace file will get executed. And then we have the relay count and the time unit in nanoseconds. So let's look at the synthetic workload configuration. So as I mentioned, synthetic workload is what is generated, or the requests are generated by the simulation engine itself. And here we see that some of the attributes are similar to what is there in the trace-based workload. And even here we provide the channel chip and die IDs and the plane IDs that needs to be targeted in this experiment. And we also have the initial occupancy percentage. And we have something called the synthetic generator type, which is how the requests have to be generated. We have two options here. One is called the queue depth, and the other one is based on the bandwidth of the or the average bandwidth of the device. This queue depth is determines how the requests have to be generated based on the number of slots available in the hardware queue. And the read percentage, we can define the amount of reads that have to be generated. And the address distribution tells us whether it needs to be random address generation, but has to be uniformly distributed across the logical address space of the device. Or we can also configure it to perform hot writes and basically hot requests, where the same or a smaller logical address space will be accumulated with a large number of requests. And we also have the percentage of hot region, which is how much of the logical address space will be considered as a hot region compared to the overall address space. And we also have generated aligned address attribute, which means that the addresses have to be aligned to the address alignment unit, which is the next attribute. It can also, if we define it as false, it will be unaligned addresses. And the address alignment unit tells us what is the size, or how many sectors should the address be aligned to. So here this value is the number of sectors. So if it's 4K, then it means 8. We'll have to provide 8 sectors, and all the addresses will be 4K aligned. And we also have the request size distribution, which means that it's fixed distribution. And we have the average request size, which is again in terms of sectors. So we have the average request size is around 4K. And we also have to provide a seed, which is the seed for random number generation. And the average number of requests in queue, which is around 16. So these are some of the important parameters that we need to provide in the synthetic workload configuration file. And yeah, so once we provide these configuration files and we run the MQSim and the workload is finished, or the simulation engine finishes the execution of the workload, it generates an output file. And this is a snapshot of the output file, but it also provides more information, which can be the details of those information will be available in the README file. And here we look at this will tell us what workload was generated for or what workload was used for the experiment. And here we see the name of the workload and how many requests were generated or were executed in the workload, which is around 7,000 requests. And we have the read request count and the write request count. And we also have throughput numbers, which are very important for analyzing the performance of the SSD. And we also have the amount of bytes transferred to the SSD and the division of read and writes. And we also have bandwidth numbers and the device response time and the minimum device response time, the maximum device response time, and the end-to-end request delay, which we discussed earlier. So these numbers are provided as part of the output file, and this will be very helpful in analyzing the performance of the SSD or the policies that are there. So next we jump to how do we use MQSim. So if you are a Linux user, then we just download the source code from the Git repository, and we compile the code using make, and we use this command to to start the workload execution or the experiment. So the MQSim object gets created when we perform the make, and then we give the SSD configuration file and the workload definition file with the following attributes. And if you are a Windows user, then there is a solution file that is provided along with in the Git repository, and this can be used with Visual Studio 2017 or later. And once the source code is loaded, we can set the solution configuration to release, and we compile the solution. And it generates an executable file, which can be used inside the Visual Studio environment, or we can again use this command to start the experiment once the MQSim.exe is generated. Yeah. So this marks the end of my presentation. If you have any questions, we can discuss that.
Thanks a lot for the presentation. At the moment, I don't have questions. So.
Okay.
Okay, and thanks, Rakesh, for a great presentation.
Thank you.
Yeah, and in YouTube as well, there is no question. So, okay, I think we can wrap up today's meeting now. And yeah, in this week, there is no particular required leading or materials, but I would strongly suggest to you to visit the GitHub repository for MQSim and download it and try to take a look at the overall project organization. And also, I think it is good to run a simple traces with the default configurations. And if you have any question in that, please contact us. And yeah, we will meet next Friday as usual. So okay, take care. Have a nice Friday and weekend.
Thanks a lot. Have a nice week. Goodbye.
Bye.
Thank you.
Thank you.